Hi and welcome to today's session on properties of quadrilaterals. Now some of you may remember a quadrilateral. The definition of quadrilateral is that it's a four-sided shape, or it's got four edges. In which case we're going to be looking at a few different types, and we're going to be defining their properties. So the first one we're going to start off with, and I'm sure that you all know exactly what this shape is. This one is a square. Square is defined because we've got four equal edges, as you can see, defined by the single dash on each one. And we've got four equal angles. This is a regular polygon, and each one of these angles is a right angle or 90 degrees. As you can see, it's got four lines of symmetry, and it's got rotational symmetry of order 4. Our next shape is a rectangle. Now, this is very similar to a square. We've got four equal angles for this shape as well, or right angles or 90 degrees, but we've got two pairs of equal length edges defined by single dashes for these two, double dashes for these two. So these two are the same length, these two are the same length. Now this has got two lines of symmetry, and it's got rotational symmetry of order 2. This next one is one which I sometimes mispronounce. It's called a parallelogram. Now, the definition of parallelogram is that it's a bit like a rectangle, but slanted on its side, in which case we've got, again, two pairs of equal length sides or edges, but these sides are parallel to the lines which are opposite them. And it's got rotational symmetry of order 2. These arrows define that these two pairs, this pair is parallel, and this pair just across here is parallel. So we've got 3 more types here. The first one is a rhombus. Now a rhombus is a bit like a square, but it's been squashed, in which case the edges or sides are all equal. And we've got two lots or two pairs of parallel edges. But as you can see, where the diagonals, drawing lines for the diagonals, where these bisect, it creates right angles, creates 90-degree angles. And it's got two lines of symmetry, and it's got rotational symmetry of order 2. Now this one is a trapezium. This is a non-isosceles trapezium. So all that it's got, the definition for this is that it's got one pair of parallel sides, as you can see here. As opposed to an isosceles trapezium, both of these are still just trapeziums, but this one's just got a bit more of a definition to it, because we've got a pair of equal length sides which make up almost the stance to the trapezium, but still the top and bottom lengths, these two are parallel to each other, and this will have one line of symmetry. 2 more. Here we've got our kite. So a kite is pretty much made of 2 pairs of lines which have got equal length. So here we've got one, and here we've got another. Here we've got one, here we've got another. And where the opposite vertices bisect each other, it creates right angles, 90-degree angles. And it's got one line of symmetry, just going straight through here. And our last one is our delta. It's also called a narrowhead, as you could probably identify from the shape. For the Star Trek fans, I think this is a similar shape to the badge that used to be worn on the chest part. But this is very similar to the kite, where with the kite, this part is pushing outwards. On a delta or arrowhead, this is flipped on the inside. So again, we've got 2 pairs of equal side lengths, but we've also got one angle which is going to be greater than 180 degrees, and drawing a line through the vertex, opposite vertexes, vertices creates a right angle, 90-degree angle, as you can see at the bottom here, and you'll have one line of symmetry. Now, we can use the facts of the internal angles of a triangle to calculate the angles in polygons and especially quadrilaterals. Just prove to ourselves that a quadrilateral has all the angles on the inside add up to 360 degrees. So here I've got a quadrilateral. If I was to split this quadrilateral in half, or just connecting the two of the vertices together, as you can see, we've created two triangles. Now, I know that this is going through an algebraic proof. You can take a bit more look at this, but pretty much we know that the internal angles of a triangle is 180 degrees. So if we've got two lots of the triangles doubling 180 degrees, that means the sum of the angles are 360 degrees. And this will work on any size polygon. If you want to split it up into triangles, you can then identify the sum of the angles and thusly from that calculate what individual angles will work out to be, especially in regular polygons. If you like what you see, please subscribe. Thank you very much for watching.